In today's discussion, we are going to talk about how do we generate a wideband FM. For a narrowband FM, in our first lecture, we presented a block diagram, and from the block diagram, it is quite easy. We just need some integrators and amplifiers to eventually achieve a frequency modulated signal. But for wideband FM, we have two specific methods. The first one is the direct method, and the second one is the indirect method. Previously, we have discussed little bit about the direct method, and we would revisit it again today. Let us now consider a very generic model for the generation of frequency modulated signals. Specifically, given that we have a message signal m of t, so we can modulate this in terms of a frequency modulated waveform by utilizing the generic expression which is given here. Note that this message signal should pass through an integrator, multiply with a sensitivity constant kf, and then it would add with the carrier frequency omega c, and this whole thing would go through would be treated as an argument of the trigonometric cos function, which is then multiplied with the gain, and then the whole of this would be eventually the frequency modulated signal. Now I have made a small simulation to generate or to simulate all of this using Simulink platform in MATLAB, right? So initially, for the message signal, what I have considered is I have considered a triangular waveform that is oscillating at a low frequency, because this is a message signal or a baseband signal. So I have set this equal to 4 pi, and then we have omega c, or the carrier frequency. Now this is at a higher frequency, so I have made a block of constant. This is omega c, which is operating at 50 hertz, right? So next block is the sensitivity constant kf. So for that I have multiplied the trigonometric input signal, or the triangular input signal, with this gain 50, which represents kf. Now omega c plus kf into m of t, right? Both of them, so this block m of t times kf goes into our summation, and similarly omega c, which is a constant block over here, that also goes to our summation over here. So this is simply a summation block. After that, whole of this summation goes through an integrator, which is represented in terms of its Laplace notation, that is 1 over s. So this block is for integration. So this the upper fed signal and the lower fed signal, both of them pass through the integrator. Since this is constant, omega c is constant, so if it passes through an integrator, so what we would have is, if this is fc, if it passes through an integrator, we will get fct over here, right? So we can just express it. If this is fc, so we would have fct here. Similarly, we would have over here kf m of t, right? And once it passes through an integration, we would have kf integration of m of alpha d alpha, and the integration is from minus infinity to t, and this whole thing would be divided by 2 pi to be in par with hertz rather than radians per second. So to make this equivalent to our original equation, so we multiply whole of this input with 2 pi, so that we have 2 pi fct, right? Remember, we would have plus the integration of this over here, right? So once we pass it through the gain of 2 pi, so we would have omega ct plus kf, then this block, which we often refer as A of t. So this is then fed to a trigonometric function which we have used as a cos function over here, right? So the whole of this is basically the argument of this cos function, and then the cos function itself is multiplied with the gain of 1, which we have expressed here. So in our case the A is equal to 1, and then we have fed this to a scope, right? At the same time, we have fed our original signal to the scope, and the output of whole of these operations is also fed to the scope. Now in simulations, let me go back to the simulation to get a better picture. So in simulations, what we have is this yellow plot is giving us the triangular function, which is the input, while the blue oscillations is the frequency modulated signal. So as the amplitude increases, the oscillation would increase, and as the amplitude decreases, the oscillation would decrease, right? So this is a generic model for the frequency modulation. Note that what we can do is we can consider all of this, anything above the message signal, as a voltage control oscillator. So voltage control oscillator is nothing but a frequency modulator. So based on the amplitude value of the incoming signal or the message signal, the instantaneous frequency is adjusted, right? So this whole thing is direct method, that is the voltage control oscillator using the VCO, right? So in the direct method, as I mentioned before, we have the message signal which is controlled using a VCO, voltage control oscillator, which is also called the frequency modulator, and then we at the output we have GFM of t, that is our message signal, GFM of t, right? So it is very simple in design. So if it says that your input signal is, based on that input you would get the output signal. However, there is a disadvantage, and the disadvantage is in terms of the carrier frequency, which often drifts. From the circuit point of view, we can use the voltage control oscillator with varactor diodes using this diagram, this circuit diagram. So in this circuit diagram, it's a very simple circuit diagram. We have a transformer. Initially we have an input X of t, and then we have a transformer, which is a step down transformer, and then we have a radio frequency choke, RFC. Then we have a DC block, or simply a capacitor. This is simply an inductor, this is a capacitor. Again we have a capacitor in parallel and inductor in parallel, and then importantly we have a varactor diode, right? So let us go one by one. So when your input signal is fed to this circuit, it passes through this transformer which regulates the low frequency, and then we have an inductor in series which takes care of the high frequencies, or it rejects the radio frequency. So that's why we call it the radio frequency choke, right? So it rejects the high frequencies. We also know that if there is a capacitor in series, so what it would do is it would block the DC value, or simply in a circuit it would reject the average value. So this is basically the operation of our DC block. So we are left with the components capacitor, inductor, which are in parallel, and importantly we have a varactor diode. So this is the most significant component when we are designing the voltage control oscillator. The reason for that is this is the only component, the varactor diode is the only component whose capacitance varies with respect to the incoming message signal, which we have represented in terms of X of t, right? To understand the working of this circuit, let us look into the oscillation frequency, or simply the instantaneous frequency. So instantaneous or oscillation frequency, that is omega naught, and from here we can say that this is equal to 1 over under root inductor and equivalent capacitance, whereas the equivalent capacitance C is equal to C naught minus K M of T, where C naught is the fixed capacitance which is obtained from here and from the nominal value of the capacitance of vector diode. K is the constant which deals with the sensitivity of the perturbation in equivalent capacitance using M of T, right? Of T and X of T both represent the message signal. So using the above expression, we can express omega naught as 1 over L C naught, and then in fact we have expanded the C in terms of C naught minus Km of T. So resultantly what we would have is we would have 1 minus Km of T by C naught. Note that we have extracted out the C naught, so this would be simply C naught by C naught, which is 1 here, and Km of T by C naught, which is over here, and to cover for the square root we would have 1 by 2 plus, since it was in the denominator, we would have a minus sign here. So next in line is we have one strong assumption that we are going to utilize next, and that is that we say that K M of T by C naught is much smaller than 1. So if it is much smaller than 1, so what we can use is we can use a binomial expansion. And for that we have simply 1 plus x power n is equal to 1 plus nx, provided that x is much smaller than 1, right? So we would have a converging series, and for that we are just going to take two terms. So this is an approximation, and higher order terms would be converging to 0 or would have a very small value. So based on this intuition, what we can have is we can express omega naught as follows. That is 1 over the square root of LC plus 1 over square root of LC times Km of T by 2C naught, right? So this is our free running frequency, or omega C, plus this again is omega C, which is multiplied by K, and then it is divided by 2C naught, and this whole is multiplied by the message signal M of T. We can simplify it further by expressing this in terms of a variable that we have previously used for the sensitivity of frequency modulation, that is Kf M of T, where Kf is equal to omega C times K by 2C naught. Also previously we have mentioned that the equivalence capacitance C is equal to C naught minus K M of T. This block over here is giving us the change in capacitance value, right? And the maximum change is simply delta C, represented by delta C, which is a very simple expression. That is, if you maximize this block Km of t, so Km of t, so that value would be delta C, that is the maximum change. So when this is maximum, right, the change would be maximum. So if it is m of t is at the negative peak, so the negative peak with this minus sign will become positive and you would have the maximum change, or other way around, if m of t is positive, if we multiply with the constant k, so in that case the major chunk of the capacitance will be removed from C naught. The solution for this expression is actually quite simple. So the maximum would correspond to the maximum value of the message signal, and the maximum value of the message signal is simply MP, whereas K is a constant, so that would not play a big role in the maximization of this whole function, right? So for K, we can equate K in terms of Kf as follows, that K is equal to 2 times C naught Kf over omega C. So this is our maximum change in capacitance. But remember, previously we have said that Km of t by C naught is much less than 1, and based on this assumption we concluded that we could use the binomial expansion to achieve a converging series, and then we used only two terms, the first term and the second term, to represent all of this in this equality, right? So based on that we can do some sort of normalization, which suggests that if you normalize it, that is delta C by the constant value of capacitance C naught, so this is equivalent to 2kf by omega C MP. And to remove the harmonic distortions, what we would need is, we would need delta C by C naught to be much less than 1, so that it is in accordance with our binomial expansion. So in short, what we have used is, we have taken a simple circuit and induced a vector diode which has variable capacitance determined by the incoming message signal. We have removed the higher frequencies, we have regulated the low frequencies, and we have removed the average value, and based on that we have an equivalence capacitance, and from there we derived an expression for the instantaneous frequency omega naught, right? And the deviation in capacitance, and we have said that our analysis is valid for this condition, that delta C by C naught is much less than 1. So this is a simple circuit, but as I have mentioned previously, this whole thing is VCO, but this has a tendency to encounter a drift in the carrier frequency omega C, which is problematic. And for that reason, the older or the conventional frequency modulators are not using the direct method, and instead they are using an indirect method, which we are going to discuss next.